Good evening. As it says, and as Bill said, I'm Alastair Bennett from Rainbow Technology Systems up in Glasgow. I'm one of the mechanical design engineers with the company. I know quite a few of you were probably up visiting us in May when we had one of the seminars up there. The astute amongst you will have noticed that the title has changed from what was originally advertised. We're going to look at the environmental effects and phototools, but our research on that's still ongoing, so we're hopeful we'll be able to talk about that in the future. But for tonight, we're going to look a bit at liquid resist technology, and specifically the 100% solids UV-curable liquid etch resist that we use at Rainbow and that we've been working with for a while. A brilliantly misleading name in the use of the word solids there, because it actually stays liquid throughout. A bit of background first. I started out studying product design engineering. I got a master's in that from Strathclyde University. Pretty much bang in the middle of my degree, there was a credit crunch, which was a great thing when 2 years later graduated and there were very few jobs to be had. Moved down south, worked with Cardiff University and Ford Motor Company for something called a KTP, which a few of the companies might know about, knowledge transfer partnerships, which, just following on from what Steve said, they're a great way of getting people experience in all sorts of industries. They're kind of aimed at people who haven't had a job in industry before, and they link you between a university and a company to work. And then finished the project there, moved up and became a design engineer at Rainbow a year and a half or so ago. Feels a bit longer at times, but that's just how it goes. So just have a quick outline of what I'm going to talk about quickly. I'll look at current resist technology, so dry films and liquid photoimageable resists. A bit about previous attempts at 100% solids, which we'll just refer to as solvent-free, because it's easier to say from now on. And then just do a few comparisons, looking at things like film thickness, conformity, tenting, dust and debris, and environmental impact of the processes. So dry film and LPI, very well established processes, which I imagine quite a few people in this room are used to using. Very good at what they do, but they have their pros and cons. So dry film, pros, things like it's applied, ready to use, comes in ready to apply, ease of handling because it's not a liquid that you're working with. You can get tenting on features that you're working with. But there's issues with conformity of what you're working with, the thickness of the resist you're using, and the energy needed to cure, and links to the cost there. Whereas with LPI, you get a thinner film weight, which you don't get with dry film. You get conformity to your surface because you're working with a liquid, and some cost improvements. But on the downside, compared to dry film, you need to dry it, pre-dry it with an oven. You've got solvents that you need to remove. You've got micro-cracking that can occur because of those solvents. You can't get tenting with it, and you need, again, a reasonable amount of energy to cure those solvents. So solvent-free liquid resist, which I'm going to kind of focus on, there were previous attempts made by companies like Grace to work with these resists a number of years ago. But there were a number of issues with that. The main one being that they could only get it to work with an off-contact process, which immediately brought in issues, particularly for the resolution of what they could produce. The UV drying time was still quite high, and the energy requirement was high, so it didn't have that many advantages over the dry film and LPI. Whereas what we're working with just now up in Glasgow, we're now working where we can have direct contact between the resist we work with, the solvent-free resist, and the phototool. So a number of benefits from that, but one of them especially is the low energy that we need to cure the resist. So just some comparisons between them. In terms of film weight, dry film you can see 25 to 35 microns typically for the film that you're laying down. LPI, a bit thinner than that, between 8 and 15 microns. Whereas with the solvent-free, we've been working with 5 to 6 microns film weight on panels and getting good results with that. Obviously, you get improvements there. If you look at typical coverage, the solvent-free compared to the LPI is up to between 3 and upwards in terms of the coverage that you can get per square foot with the resist. So that gives great improvements in terms of waste as well as what you actually need to use. One of the great improvements that we see when we're using this over the kind of traditional processes, if you will. On the left, you've got your kind of sandwich that you'd be creating when you're working with dry film. compared to on the right what we're working with when you're using the solvent-free resist. So you've got the blue layer in each, dry film around 35 microns, compared to with the wet resist we're using down at 5 or so microns. On the left, in the dry film, you've got a protective mylar layer. It could be 25 microns, which we don't have. And then you've got the protection film. It could be 9 microns for dry film. We're currently working with about 3 microns on the photo tools we're using. So some very simple maths, because it's just addition, is 69 microns for the dry film versus 8 microns for the solvent-free. So it's about 8.5 times thinner when you're actually just sandwiching it together for your process. And in terms of what we can produce with that, if we're wanting to produce, say, a 20 micron feature onto a panel, we've got the same as before. So we've got the dry film. On the left, you've got the mylar, then the protection on the photo tool. Compared to on the right, just the resist and then the protection on the photo tool. If we use a 6-degree half-angle light source, which is not particularly collimated, by the time that comes through a 20 micron feature, we can be growing up to 34.5 microns with the dry film compared to just 21.7 for the feature once it's printed, which doesn't, well, it sounds much scary if you make it a percentage. So 172.5% of what you're looking for compared to 108.5% with the solvent-free resist. The other advantage that we've seen with this, we're working with this 6-degree half-angle light source. Because it's not as collimated, if you get dust or dirt into the feature when you're trying to print it, the light just goes around it. It doesn't cause the issue in the resist when you're curing it. Another great improvement we've seen is with conformity. Obviously, you don't get this with the dry film, you get it with the LPI, but this is an image that we got taken with a SEM electron microscope of one of our panels we'd printed. You can see all the bumps in the copper and make out the roughness of it very well. And these are 10 micron track and gap features we've been printing. But you can see if you look at the edges where there's bumps and very rough patches in the copper, the resist, because the liquid flows over it, giving you a good contact, especially when it comes to etching. But also because we don't have the solvent in this resist that we're using, you can go down to these fine features, and when you come to dry them out, then you don't get micro-cracking occurring, so it's not trying to pull away, and you can get those small features to produce very clearly. Linked to that micro-cracking and the solvent, or lack of solvent in the process we're doing, we can achieve tenting using our liquid resist, which with the LPI you can't because it'll dry out and crack. When we laminate on and then when we cure the resist, we're going from a liquid to a solid instantly. With the solvent, it kind of it loses its structure and falls apart. You can't get your tenting over features to work properly. Whereas with this, we're going straight to it. These are 900 micron features that we've been tenting just to test stuff. We've also been doing 4 by 6 millimeter slots in panels and getting those to tent successfully. So that's just something, you could do it with the dry film, not with the LPI, but we can achieve it with our liquid that we're working with just now with the solvent-free. Dust and debris, because we're working with photo tools and a liquid resist, is clearly a big issue that people are concerned about. So we thought we'll do some experiments, see what issues we're actually coming across with it. So on the left, you can see a panel that's laminated. We took a panel, we laid down some solvent-free resist and introduced quite a large amount of debris deliberately into it before lamination. We laminated it and cured it, and that's the image you can see on the left there. It's not as clear on the screen, but you can see all of the debris that was cured into that ink. We then peeled it off as you would as standard, and the image on the middle shows the panel, and the right shows the photo tool. It's hard to see because photo tools, from my experience, are quite hard to actually get photos of because they're so shiny. But when we examined it, all of the debris had gone with the panel because of the way it cured, not with the photo tool. The release coating on the photo tool had let go of all of the debris that had gone. So when you're working with this solvent-free resist, you're not going to get any repeat defects as you go panel to panel. And one of the big ones, especially Steve was talking about Steve was talking about China earlier, and there's a lot to do with the environmental impact and what they actually have access to out there when they're running their factories. With the solvent-free, you've got a number of advantages in terms of the environment. So because there's no solvent to remove, we're reducing the amount of energy we're needing at the state throughout the process. As with, because we've got no pre-dry we need, that's less energy needed, and the time that we actually need is reduced, so that helps with your production. The resist itself needs less energy to actually cure it, so 2 millijoules compared to 50 to 100 millijoules for the actual curing, so we've got far less energy we need to put in at that point, and far less time for developing it. And in the development, because it's a liquid rather than a solid or a gel at that point, the development's almost more of a wash-off because it just comes out so much easier. And because you've got a much thinner film weight to work with, it's much easier. You're spending far less time actually having to get it out. And again, because you've got the thinner film weight, the amount of waste that you're actually producing is massively reduced. So a quick summary. The solvent-free has a number of advantages over dry film and LPI. You've got thinner film thickness that you can use, and we can also get down to smaller feature sizes using it as opposed to dry film or LPI. Tenting capabilities and conformity to surface, we can achieve both using solvent-free liquid resist as opposed to achieving one or the other using dry film or LPI. And there's a very big change in the environmental impact. We're massively reducing the amount of waste and energy which we're using. Yeah, so that's all I had to say, really. Has anyone got any questions? Which I'm slightly worried about saying, but you know, let's go for it. Yes. How do we apply the resist? We apply it just now in one of two ways. For one of our processes, we've got a roller coater that we use to apply it to both sides of the panel at once. And with one of our other ones on the desktop coater, we apply it and then use a Meyer bar to apply it over the substrate. Thank you very much.